Welcome everyone to Acreon tutorial series, quarter car, H infinity control from road disturbance to robust ride. Um, and in the first part, I modeled the quarter car wheel system, which was a spring mass damper system with an active hydraulic cylinder in the suspension, and the chassis was modeled as one mass component, the wheel was modeled as another mass component, and the tire itself was modeled as basically a spring, modeling this tire stiffness here. And then in this part, I'm going to just briefly recap the dynamics of the perturbed equilibrium model that was derived, and that's how the state space was assembled. And then I'm going to go to that state space system and then perform analysis and do the same thing as the cart pull series with respect to observability and controllability before stepping into the H infinity control, which would be first starting with static weight, H infinity state feedback, and then go into observer frequency shaping and then mix sensitivity. All right, so let's step into it. So again, the first part, we had that sprung mass from the suspension, the unsprung from the wheel mass, the suspension, which had the spring and the dash pot. We had a tire spring, and we had that hydraulic cylinder actuator between the body and the wheel. And so here's enumerated all of the coefficients that I'll be using in this notebook. Note that the body and the wheel are the two state variables that are in the perturbed coordinate system. ZR is the road displacement, which is that disturbance about the road, which impacts the tire, the suspension, and the body in that kind of kinematic chain order. And the state space model below is the perturbed variables that we derived earlier. And these are the two second order differential equations derived. So the first one is the mass of the body times the acceleration of the body is equal to the force of the cylinder subtracted off of the spring coefficient by the suspension displacement, and then the dash pot again with the displacement of the velocity of the body subtracted by the wheel. And I had the free body diagram pointing where the displacements were, which were in the positive z hat direction, and the forces obviously would oppose that, starting from the top down. The mass times the wheel, x double dot w. So this is the second ODE here. We have the cylinder then pushing down on the wheel, taking that spring of the suspension here, the dash pod of the suspension here, so obviously opposite signs, and then we have the tire then, which is I think it was pushing down, right? Yeah, we have a positive displacement up, the tire spring is pushing down, so that elastic body for the road handling. So these are our two ODEs. And then, like before, this is just the initial boilerplate for getting the all the Python modules in place. I'm using some SciPy, using NumPy, control. This is what I've compiled together for this tutorial series is the Acreon quarter car wheel. So like the cart pole itself, I have a smaller control set compiled into this Python module in my pip wheel. But it's going to follow a similar flow as before. We have the same kind of pole plots, Bodie responses now, since we're going to be analyzing frequency domain, similar step response, state trajectories, and the shadow price summary, which I introduced in the last video. So let's import those modules. And then here for the let's see. So this is, again, just showing off all the controllers that I've synthesized, or I shouldn't say synthesized, I've compiled for this Python module pip wheel. So we have H infinity, state feedback, state observer for the disturbance side of things. I have a dynamic weight feedback, which I'm going to introduce different performance criteria to actually shape the objective criteria of ride comfort. Kind of a similar notion with the R matrix and optimal control for reducing or penalizing control effort, and just kind of different criteria. So you get a little bit of this like Pareto, optimal frontier kind of objective shaping. um, I'm not gonna, I compiled in the polytopic stuff. I don't think I'm gonna touch on that in this tutorial series. I did that in the cart pull for uncertainty modeling. But essentially what that would capture is, again, the vertex-based plants that you can basically step through, and you could use different I don't know, noise models essentially. So you could distribute like Gaussian noise of the plant, or perhaps even like Poisson if you want, whatever. It just needs to be a convex set. And then we take the intersection and we can synthesize controllers based off of those LMIs. I'm not going to do that though in this tutorial, even though I compiled them in. I wasn't sure at the time. And then I have H infinity mixed sensitivity. So these are the main guys that I'm going to be stepping through. Okay, so that's just a brief interlude into what I'm going to be focusing on this section. So the state feedback and open loop analysis. So our, oh shoot, I've been mixing these. So these should be, the way I've been modeling this is actually Z. So let's just push this as Z dot Z. This is Z again. Sorry. Okay. And then this is Z. All right, I'll just have to make sure my markdown is okay. Anyways, all right. So our state vector here is that interleave. So we have the body state perturbation. That's a displacement. And then we have the velocity of that state variable. Similar thing for the wheel. This is just transposed. So it's a column vector. We have a road disturbance, which is R. I think I just said ZR above. I'll just leave that as is in meters. The actuator force is that cylinder, and I broke it out, if you remember, in the previous video, where part of it was having a static preload component, and then the other part was actually the actuator force component. And so this is the actuator force component. The preload is bundled into this perturbed state coordinate system. Okay. And that's why the mass, or the gravitational potential energy, even though I didn't do Lagrangian, is actually implicitly involved in this coordinate system. So we're really just dealing with the springs and the dashpots and forces of the road disturbance and the control cylinder, or the hydraulic cylinder. And so this state space, we have Z dot AZ plus B W W plus B U U. And that was, again, defined in the last video. This is just plug and play here for getting the correct plant state dynamics matrix, the control, well, the input for the disturbance matrix, the control input matrix here. And then this is a little bit newer. So for the observer side, I'm defining a C here. Again, an output space, so not the performance criteria or anything like that quite yet, but it is going to be leveraged for that. This is actually going to be the suspension travel. So we have XB minus XW. So that suspension, basically kind of like a mechanical limit here. And you can say model these as, before I had it where there'd be like absolute displacement in the cart pull example. But then here you could say, you could basically give two similar sensors there, and we're just taking the difference as this first output variable here. And then the second one is the velocity of the body, which again, you could assume perhaps there's like a IMU or an accelerometer. We integrate, get the first velocity component there. And so these are our two output variables in Y output space. And these will tie in more directly to the performance criteria later. Just note that these are in Y, not in that ZP space quite yet. Okay, so I have a pickup truck, and so I was I actually had ChatGPT kind of just generate a little bit of some interesting pickup truck, light truck, uh, coefficients here for the mass of the body, wheel, suspension, wheel rate, uh, right? The tire stiffness. So just kind of some parameters there that would be on the spring mass damper system of, a light pickup truck. It's not like that they have well, at least maybe like the fancy monster trucks or whatever would have like the active component, which that actually kind of interesting. I digress. These are the coefficients I'm running with. And we could just briefly see that the body is significantly heavier than the wheel. And then these are the relative springs between the suspension and the tire stiffness and the dash pot here of the suspension. And then similar thing, this is just for the plotting that'll happen later. So state labels, measurement labels that I described, units. And then I'm just printing off um, these coefficients, I guess, for posterity. And so here I'm setting up the A, BW, BU, and then the B, which is this horizontal concatenation of the BW and BU as our input matrix B, which takes in W and U for that concatenated exogenous input with control. And that's just, again, straightforward from what I described above. CY, same thing. DU is just going to be zeros, so there's no feed through at the moment. And that's just printing it off. Okay, so here we have the open loop poles. So the body balance, the wheel hop modes of the passive suspension. So there's no active control at the moment. So we're just analyzing basically if you were to cut that out of the free body diagram, this would be just the spring mass damper system between the body and the wheel. And so closed loop, or sorry, open loop stable. Yes, we have complex conjugate pairs on the left half plane of the continuous time model. Two are actually pretty close to the origin though, so that's obviously something to be careful of or be mindful of. But again, this isn't the closed loop control system either. So now let's step into this part where we're going to look into the controllability. Again, similar to the cart pull side of things. So if we look at Cayley-Hamilton controllability matrix, we're asking the question, binary yes or no. Is this concatenated C that's short and fat? Is it full rank? Yes or no? Yes, it is. So we have 4, 4. So it is controllable in that sense. And then similarly, I'm just kind of following the same playbook as before, just to reinforce some things. So the one difference, though, I guess, from the cart pull, I think I was just looking at the dominant modes. This one, I'm actually going to take the dominant modes and the weak modes as well. And when I say modes, it's in the eigenspace. It's not in the modal space, which I could maybe do later. But anyways, this is essentially the same exact thing. We're going to look at the controllability Gramian here. And again, just to reiterate, it indicates how strongly the actuator energy reaches different state space directions. Actuator. So we're not looking at the road disturbance at all. We're just looking at the control input of the spring mass damper system with the hydraulic cylinder. So again, large eigenvalues indicate the directions that are easier to move, small, opposite, requiring more energy. Yeah, I guess that's one thing to note is the basically the units are obviously not all consistent. One thing I am doing, I'm jumping a little bit here, but with the optimization, so I am going to go to order one and actually non-dimensionalize things here, and that significantly improves the solver results. I don't know why I just didn't do that the last series. I think maybe the system is just a little bit more simple, under-actuated. It was non-linear. I did linearize. I digress. I was playing around. I think I wanted to show more of the solver tuning. This, though, is probably the more appropriate approach where you just not dimensionalize and scale things. Again, I'm jumping the gun a little bit. That'll be in the next part. I don't know exactly why I went off. Oh, the physical units, right. So, and here, so I am just using the raw physical units. So a little bit misleading. I think it's still the intuition carries though between the strongest modes and the weakest modes of this controllability Gramian. Again, eigenspace of that, which is, we can, with when we scale the eigenvectors, we can then get a nice heat map is what I'm going to portray of what states are easier to control, what states, and when I go to the observability, the same exact thing here. So, and this was set up in pretty much the exact same fashion as the cart pull example. Maybe a little bit of, no, I think it's pretty similar. Okay, so I'm collecting the weakest dominant state impacts and then the eigenvalues suite there. However, I don't think I'm plotting the eigenvalues anymore, so I took that plot out. Anyways, so let's look at. So I'm storing that off for the time being because I'm going to do a 2 by 2 plot below the. So let's look at the observability now from the suspension travel and the body velocity. So this part's a little bit different. Whereas the cart pull example, I was just looking at those like basically raw displacement of the state variables of the pendulum angle and the cart position. This one, I'm making it a little bit more interesting where we're actually looking at the suspension travel as a function of that difference between the body and the wheel perturbed coordinate system. And then we're taking the velocity component of the body. And those are going to tie more nicely into the H infinity state feedback, which will happen next. So here's the observer part. So same thing. I kind of jumped the gun. So we have tall and skinny. It's in the adjoint space. Um, so we're asking the question now, does that see the information that we're encoding? Does that give us enough information to reconstruct all four states? So because we have Y, we want to reconstruct essentially that X hat in the perturbed coordinate system. Does this encode enough information to do that? In the binary sense, yes, it does. In the finite time observability Gramian, so again, similar thing as the controllability Gramian, we're asking how much observability, how does the observability Gramian measure how strongly each initial state direction appears in the two displacement measurements. This was, I apologize, I copied this from the previous part poll. How strongly each initial state direction appears. What did I say? I'll just say that. I'll clean that up later. Okay, so how much the initial state directions appear in the output directions. So here we have large eigenvalues, identifying the state combinations that are strongly visible in Y, and then small eigenvalues are weakly observed combinations that are more sensitive to measurement noise and model error, thus indicating that they're harder to reconstruct that X hat that we would then use for state feedback control. I'll touch on this in a moment. This was just a precursor to the 2 by 2 description and the result there. So this is again setting up a similar thing here. What I actually might do is this really quick. So I'm going to do this markdown, and then I'm going to move you down here. Okay. Okay, so we got the observability Gramian encoded, and this is exactly the same thing. So we have the sweep, we have the weakest state impact, dominant state impact, and then this will be just a brief analysis here. So Gramian and observability Gramian analysis. Okay. Okay, cool. So I'll plot this. How should I do this? Man, kind of apologize for just kind of coding on the fly. I try to get it so it's a little bit less. Coding on the fly can be a little bit annoying for followers, so I have most of this pre-done. Anyways, so um, I'll plot first, and then we'll go back. So here's the finite time, Gramian, weak, and dominant modes. So we have the controllability, the weakest modes here, the plot in this upper left-hand corner, the dominant in the upper right, the weakest observability bottom left, and the weakest or the dominant observability on the bottom right. Essentially, what I'm saying in this blurb above here is that when we look at the ODEs, actually, I'll scroll all the way up to that portion here. So the actuator is impacting the acceleration of the body and the wheel. And so it'll have much more control authority over the velocity channel than the displacements themselves. And then if you remember that the body, or just physical intuition, the body itself is significantly heavier than the wheel. So in terms of our controllability here, going all the way down, that matches that intuition. So the dominant controllability, the wheel velocity is much easier to excite, much easier to control in the dominant eigenspace, this mode. The wheel perturbation is not as easy to control because we have to integrate out the velocity component, and then that component or the wheel perturbation itself is tied to we're not modeling the road disturbance quite yet, but that's also going to impact. But in this Gramian dominant mode plot here, we can see that. Well, sorry, just to back up, it's the wheel perturbation. So we have integrating that velocity component, and then also we have the tire stiffness spring. So we have that component as well. So we have basically additional couplings here that make it harder to control that wheel perturbation itself. And then similarly, the body perturbation is going to be harder to control as well. And that lines up exactly with the controllability, the weakest mode, and that eigenvectors. You can see that those states are harder or more excited in the weakest mode. So that gives physical intuition there. The body velocity is a little bit easier, but again, it's much more heavy than the wheel velocity. So that's just a little bit of intuition there. So the observability now is modeled actually opposite. So that's kind of the interesting thing here. Because we are directly measuring the suspension travel now. So the wheel perturbation and the body perturbation, we actually have dominant observability that is much more observable in these two states on that dominant mode in the eigenspace here. So that is good because that will tie directly into ride comfort and mechanical limitations of the suspension and whatnot. Likewise, the body velocity too also is more prevalent in the dominant eigenspace here, this mode. The wheel velocity, though, is not. But that is the best controllable, or the most controllable state direction. And so there's kind of obviously we have observability measuring different directions in this eigenspace than the controller, but the controllability side. But that's actually kind of per design here for the H infinity uh, control. And so the weakest observability here, we can see it's definitely the wheel, and then the body velocity too. And that's just because, again, we don't have a sensor directly measuring the wheel velocity. Number one, that would be also difficult to do as well. But then we're focused more on perform. I'm getting more towards that notion of the performance metrics that I'll introduce later on. And so that's a quick analysis of the controller and observability Gramian analysis. I'll just double check if I missed anything that I wrote down earlier. Yeah. So we have road handling. That's when the road disturbance will kick in more. That's obvious. That's going to be one of the harder ones to have performance criteria fulfillment on. Control efforts like that are, I said, that's pushing down on the control cylinder energy. Um, yeah, they are still. I didn't plot the eigenvalues, but they all dissipate energy, and that can be seen with the open loop plot too being stable. Um, Yeah, and then as for mentioned with the weak modes with noise, so wheel velocity is going to have more noise, so it's going to be harder, much more difficult to observe too. So just more things to think about or consider before stepping into the control design. And I think that covers this section of this series. Appreciate you watching, and I hope to see you back in the next one. Thanks.